Oh, perfect.
All
Nice.
right.
All right, we're good. And everybody's has their permissions on. Okay. So let's get going. All right,
Awesome.
guys. Hi, everybody. Welcome to the continuation of our spring 2025 session of seminars as part of the HAG Research Group. So today we have a really special guest. We have Arbab Arshad, who's a PhD candidate at Iowa State. And he's going to be talking about, as you can see on the screen, adapting vision language models for domain applications with an agricultural focus. This isn't something that we have seen a lot of in terms of application of machine learning techniques and such. So we're really excited to hear from Arbab, our guest. So you're affiliated, Arbab, with the AI Institute for Resilient Agriculture, and your more general focus is on generative AI, LLMs, and multimodal machine learning. Please, as a plug, look into Arbab's publications, which impressively are in NeurIPS and WACV. So please look at his research, give him some love over there. And without further ado, I'll hand it over to you, and you can kick it off. So thank you once again for joining us.
Yeah, thanks. Thanks a lot for warm introduction. Yeah. So as mentioned, I'll be presenting on applications of generative AI with a focus on agriculture, and I'm affiliated with the AI Institute of Resilient Agriculture, which is hosted at Iowa State University, led by Dr. Bhaskar Ganapathy Subramanu and my PhD advisor, Professor Samik Sarkar. And it's been quite a blessing to work in that interdisciplinary environment. My major is computer science, so I'm PhD candidate in computer science. So a lot of people come together there, and I'm pretty hopeful you will have uh, some nice ideas at the end of the presentation. Uh, so let's get started. So the domain that we are focusing in is agriculture. Uh, that's that's pretty important and pretty complicated too. Uh, uh, I mean, we don't really get to see the complexities that happens behind the scene to get the food on our table, but there's a lot that goes on. And those complexities include weather changes. We have soil. We have a lot of different pests attacking food, and whatever left just uh, is what we get to enjoy. And it's quite an unpredictable environment a lot of times, especially with a lot of new climate activities going on, and a lot of it is handled by very niche experts. Um, and there's a vast economy which depends on that. So in United States, about 1.5 trillion dollars of U.S. economy, the GDP. That's agriculture. That's from 2023 survey. So to put it to scale, that's about close to 5.5% of the total economy. So it's a big number, and the challenges that we can look at as scientists try to solve some of the hanging fruits. There are the crop analysis, how the growth cycle goes on for different kind of crops, and the real-time disease detection. Disease could be from the pests, from insects, weeds, anything, or trying to understand how their growth patterns occur over time. So all this is useful information, and these could help in very genuine way to try to increase the yield of crops. So these are just a few of those venues that could be explored. And in this presentation, we'll touch on a few of those topics. Um, the first one is that we use vision language models, uh, and those language models could very well overcome the limitation that we face with the traditional machine learning models, which is that let's say you have to predict if it's a cat or a dog. Well, the first thing that you have got to do is collect 1,000 photos of cats, 1,000 photos of dogs, and annotate them, and then is what machine learning model would be able to understand what is it that we're talking about, right? So that's the way. And now imagine hundreds of diseases, thousands of crops, and tens of thousands of areas. So the problem gets very tricky. So the data annotation, where you can label, which is the first step, and once you've done that, then train the machine learning model. So that has been the traditional pipeline. But the overhaul that we propose in this work is that with the very minimal annotation, from thousands to down to uh, just couple of handful of annotations, you can achieve um, almost the same kind of performance. So, and those lessons, they carry over in a lot of different domains as well, not just in agriculture, because the model, they just see tokens, they just see numbers, but a lot of it, I'm pretty confident, could be adapted to a lot of different domains as well. But this work of agriculture is a very good use case given the complexity and the opportunity of making a difference. So the first work, that's leveraging vision language models for specialized agriculture. Very grateful for all the co-authors and the collaboration that went on. Um, so yeah, why this matters, I think that's pretty clear. If there's any question, just feel free to uh, ping me. Just pause it, and I'll be happy to explain it. Uh, yeah. So the first question is that these annotation, how do you reduce the scope of them, so that what are the tools which can help you do that? And visual language models with the few shot in context learning, and what that means is that these models, they can learn from very small number of examples. You don't need thousands of examples to be able to do that. You just have to be smart enough to prompt them in a way that they could understand. And we'll see quantitatively later on how that goes on. And the models that we evaluate for that are from all the major vendors, which are GPT-4o, 3.5 Sonnet, so OpenAI's Anthropic, Google's Gemini, and open source version Lava as well, and also the budget-friendlier options of some of those. And and the first thing that you need to have to be able to test any system is just have a benchmark ready. That is, uh, I systematically curate what are the things that we're going to ask it, and that's where we have this benchmark. We call it ag eval, and this consists of a lot of different problems. Let me give you one example. We have mango leaf disease. For example, if the leaf disease is anthracnose or it's dieback, well, these are two examples. Of course, the data set has a lot more. Just for illustration, we have two. Or it could be, what is the insect, right? Is it aphids or is it tomato hornworm? So this could be it, or what kind of a weed it is, right? And the common theme that you will notice between all of them is that we are only concerned with what the problem is, just labeling it, and that's what is termed to as identification. And we can get more granular about it and see, okay, let's see what how bad the problem is. So for example, if you look at the bottom left side of your screen, the soybean stress severity from a rating of 1 to 5. 5 means very bad, 1 means not as bad but still exist. Then uh, then now we have a ordinal value which can tell how bad it is. So that is referred to as classification in this benchmark. And then we have different of those examples that you see my pointer hovering over. And then you can get even more granular, and instead of just an ordinal scale, you can ask, okay, let's see how exactly bad it is, and and just slap a exact number on it. For example, if you see here, a leaf is damaged and you're trying to annotate if it's 3% damaged, it's 74% annotated. So now we have a way more concrete number. So overall, what this all is representing is we have a lot of variety of different kind of tasks that we can test all these models that we saw on the previous slide over here. Because the first thing in improving is to be able to understand and measure. So if you can't measure, you can't improve it. So that is the first step that you do, and systematically curate all of these annotated uh, data sets into single benchmark. Um, yeah, so just to clarify the in-context learning aspect of it, so the way these language model works is that you can either ask them out of the box. For example, if you give it the input, this movie is great. What is the sentiment? Is it positive? Is it negative? Well, this definitely sounds positive and will give you a response. But a smarter way of prompting these language models is that you give it few examples, not a lot, but just few. You give it, okay, I love it, that's positive. Terrible experience, that's negative. And now I have a new input. The movie is great. Is it positive or negative? So if you format your inputs this way, this is called few shot learning to cover the basics. The models would perform way better. So just to create the basics, of course, we are not finding movie reviews, but we are concerned about how models are performing for specific tasks in agriculture. And what we are interested in, as you have seen previously, we are trying to see, okay, what the problem is. So essentially, we're asking the model, uh, let's give it this image, what kind of disease it is, right? Is it anthracose? Is it dieback? Just tell us the output label, right? So that's our output. Our input is image, and this is how formally you can ask it. Uh, so this prompt that we give, it's pretty task agnostic. That is, we don't give any additional information uh, about about any particular kind of disease or insect. So it's pretty task agnostic. That means we just have it treated as black box classification model. So we'll just give it the image. Excuse me. We'll just give it the image, and it will give us one output label. We'll give it the options. Given the image, we'll say, is it anthracose? Is it dieback? And it's going to choose from within those varied options. So that's as much help as we are willing to give it. And to illustrate, on the right side, you can see an image from identifying the weeds. And what you can see here is that the correct ground truth is Chinese apple. So that's what is the weed that's present over here. And here we have all the models. This is just one illustration. We have we have analysis later on, but what you can see is, for example, for Gemini Flash 1.5, this second row, it initially predicted it as a prickly, but if you give it 8 examples, which is that if you feed the examples this way, image, weed label, image, weed label. You give it 8 of them, and then you ask the one about this image. Then, of course, it has learned from all of those previous ones, and it should be able to give us better performance. And that's what happened over here when we gave it 8 examples. Of course, this is an anecdotal example. Um, uh, then it predicts it rightly. So this is to illustrate how this few shot learning is working and how the whole thing is set up. If there's any questions so far, please let me know. I'm happy to answer. Um, yeah, so to summarize, we have first of all the benchmark. Secondly, we want to see how this giving few examples affect the model's performance. And we are comparing a lot of different models to be able to do that. And once we do that, then we figure out, okay, what is it actually that worked in all of the examples, but more of those details later on. The metric, of course, we have the output labels. So the standard metric there is F1 score. We have the predicted label, and we have the ground truth label. Uh, uh, we can just calculate the F1 score. So that's a pretty traditional metric. Or as you can see in the second row of the benchmark, if I can show you again over here, this one. Well, here the labels are not just labels. If a model is predicting this image that it is rating 1, well, that's worse. But if it says it's rating 4, that's not as bad. So you want to take into account that factor where if the closer the predicted label is in that ordinal scale, the better it is. So there you can't just get away with F1 score, and that's the motivation between to get the normalized mean absolute error. This metric is gonna take care of that factor. So now we have two metric. The third thing of comparison that we want is the intermodal comparison, and there we use this metric mean reciprocal rank, which is gonna just give an overall number for one model across all the tasks. So we have the formal definition given here, uh, but what it's gonna do is look at all the models and all the tasks and just gonna rank which one performed the best. Of course, if it's F1 score, the higher the better. If it's normalized mean absolute error, the lower the better. So I mean the formal definition is given here, but we can look at it when go to the results. We can refer back to it to be able to interpret better. So we have the Gemini Pro 1.5, and that's our first row over here. What you see over this side is all the models, right? You have Gemini, you have GPT-4, all the models that we previously discussed. The column is each task. So each of those boxes that you saw in the benchmark, each of that is one column. Durum wheat, somewhere here you will see weeds, those insects, and all that. So durum wheat, if you see over here, this is giving us an F1 score of 55 out the box. This is zero shot. What that means is that we are only giving the model image and asking it from valid options what it is. We are not providing it with any additional information. And what happens there is it gives an F1 score of 55. So it's not random. It's not good, but it's surprisingly not bad either. So these models, which have just crawled the whole web, and now we can ask them questions, well, they are doing as well. At the point of paper uh, publication, this was the latest model, and this is how well they were performing, 55 for this particular one. And then you have the number listed for all the task and for all the models as well. I stress on this for a reason that we'll find out later. So this first table is that identification, that first row of the benchmark that we saw over here, this one. This is referring to the first table. And of course, the metric in the second table is different, which is the normalized mean absolute error that we just motivated why we need it. And we have the numbers listed over here too. So yeah, so as I said, we want to measure how good things are before we try to improve it. And this work mainly is about that. We will try to look at it from as many angles as possible and see what are the low-hanging fruits that we can entertain. And that's what the future work is. And in the next few papers that we will also discuss today. So yeah, Gemini Pro 1.5, that's giving us a very good score overall compared to GPT-4o, uh, which is actually doing better in classification and quantification. So out of the box, that's how models are doing. But if you see at this spider plot, and to help you interpret each of this edge is a task. So the more this line is close to the edge, the better the performance is. So the more area it's covering, the better it is. And this one is the zero shot, which is what we saw so far. This is how it's looking. Some tasks performing better, some not so better. But the area does grow as we give it the examples to learn from. And if you see over here, the area has grown over few tasks, as you can see intuitively. It's just supposed to give us some bird's eye picture of what's going on. And if you give it 8 examples, now it's way bigger compared to the one on the left. So and that we have for all the models, right? Each model is represented by a different color, Gemini, GPT-4. So it's across the board that it does increase if we give it more examples. But that's a bird's eye view that we just talked about. Now I want to look into detail what actually went on under the hood. And we can start by analyzing the performance of 8 shot, which is we were giving 8 examples to the model. And here you will notice this Durham weight, which was the score 55, and now we gave it about 8 examples, just 8 examples from any 8 classes. Uh, the performance jumped to about 95, which is pretty good. Uh, so so the model is able to go uh, from just 55 to about 95% F1 score, and that's pretty impressive. That's being done with GPT-4o for this particular data set. But if you look overall, then the score grew for this model from 46% across all the tasks to about 73. So that's a remarkable progress, almost a double. So models are clearly able to learn from a lot of different examples. We don't have any filter what kind of example is it that we are feeding, just giving random examples, choosing from the data set, but they're able to learn just from looking at it. And that's an interesting phenomena. If they're just able to learn from 8 unfiltered examples, then we need to understand what is it that's happening, so that we can maybe better tune those examples later on as one use case. And then we have some nuances with respect to the classification and quantification task, which is the lower table as we talked about. But that's the phenomena, and you can zoom into each task. This is the first task, the Durham wheat. This was at about, if you can pay attention to my pointer, about 55%. But then you give it more examples, and then it soars all the way to about 95 for this model, GPT-4o at least. And the other models also perform very well. It's just that some model they are just able to learn a lot faster compared to other models, given the examples, and we quantify that phenomena too. But what you can see across the board is that for each model given here, the values are increasing, and that's true for almost all the tasks, right? Because the higher the F1 score, these are all the blue ones, the better. And the classification and quantification, there of course the lower the score the better, and that's what happens apart from just few exceptions, which could be noise or there could be more reasons to it. But that is an encouraging trend, where we go from 0 shot to about 8 shot. Yeah, so as I pointed out, so the examples are making a big difference. So what we want to do is analyze in detail what kind of examples are actually making a difference. And there we have this definition just to distinguish the examples given. For example, if we're trying to predict cats, just to make it easier to illustrate, and you give it examples of dogs and donkeys, well, that might not help in identifying cat. But if there's a cat in those 8 examples, then it should be able to pick up on those signals and be learned from that. Uh, that's a hypothesis, and that kind of example where we do have the exact label that we want to predict to just happens to be there, then that's bullseye shot, right? At least one from those 8, just one. That's all we need. And if there's no examples and all are unrelated examples, that is, we are essentially adding a lot of noise to the model. If we're trying to uh, make it predict butterflies, but we are giving it all the different breeds of dogs, well, that's not going to help. So that's a lot of noise. Then the interesting question there is, we are feeding examples, we don't know what the actual ground truth label of the question is, because that's a chicken and egg problem. Then would the model be able to discard the irrelevant information? So that's also an interesting aspect to look at. But yeah, so that's the bullseye shot, which is that we have the example that we're looking for. We're trying to predict the cat. Well, we have one example that is related to cat. Of course, we're not predicting cat. We are predicting very niche agricultural problems. But just to illustrate, that's what's happening in the bullseye shot. And here we have the numbers. The baseline over here, this first column is what you see, 51. And then you have two different subcategories in this table, which is bullseye shot and then which is non-bullseye shot. And bullseye shot, as you know, they have those examples. And if you give that, then you give an overall improvement from those examples about 15%. across the board, right? Overall average of 1 shot, 2 shot, 4 shot, 8 shot, right? So 15% performance. But if you have examples which were not related to the input that they were trying to predict for, just completely irrelevant noise, then the model is able to just separate the wheat from the chaff, and it does not affect the performance of these vision language models on average. So that's a good news because now we can have a lot of examples, and these models can literally pick that needle from the haystack, and the more the examples, the better. So that's an insight over which a lot of later work is also built on, but that's how you can see it clearly be justified that the behavior of these models is pretty robust with respect to examples. We have another uh, phenomena being quantified. There's a lot of depth to it, but respecting time, I would try to cover the rest of the things too. So we have this phenomena. For example, in traditional machine learning, what would happen is that if a machine learning model is performing well for one class, well, it's gonna do same for the other class too, right? Uh, so uh, so yeah, I mean, uh, if it's predicting an animal class for predicting cats, well, it's gonna do 90%, let's say, for cats. It's not gonna go 40% for dogs, right? So that's those machine learning models. They had balanced data. We did not have that problem. But but as you but as you know now, these visual language models, they're trained over the entirety of the internet, and there's no balance there. Just some things happens to be more than the others, and that gives rise to the problem where these models are able to do way better on some categories compared to the other categories. And to quantify that phenomena, we have the coefficient of variation, which is defined formally on the right side. But it's going to measure that within one task, where we're trying to, let's say, identify weed 1, weed 2, weed 3, weed 5, is it performing consistently across all the weeds, or is just gonna do well with some and leave the rest of it, right? So that's the motivation behind this. And here is for one task, you see this each color. Let's focus on this Gemini's color, this first bar over here. So healthy, it's able to predict very well. But if it's bean rust, well, not as much. The model drops in performance a lot. And then, of course, it does improve if you give it few shots, which is what these slated line 8 shots is. But the trend is same. That it's not going to perform well across all the different varieties. Uh, 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 and This is the illustration of all the tasks, where you can see on left side the highest performing category within a task has way more performance compared to the lowest one. And that's not necessarily a good news, but that's a good thing to quantify. And we do that for all of these different models as well. The highest one for GPT-4o, sorry, the lowest one for GPT-4o, and the highest one with Claude 3 Haiku, which was the budget-friendly option from Anthropic. So yeah, so these were few insights that we build on, and and we have this conclusion uh, where we have the F1 score increasing from 46 to 73 if we give it few examples. And those examples which made the most difference were the bullseye shots, and we draw the difference between them there. And then we quantified the coefficient of variation, which is a phenomena which can affect some classes more than the others, because models are trained just on asymmetry of information over the internet. And then we have the nuances between the classification and quantification task, where we needed more granular details compared to just identifying what the problem is. So what models are performing better in what cases. So all of that is present in our paper, leveraging vision language models for agricultural tasks. So so yeah, that that happens to be it. So The next thing is that how do we, so that's most of our groundwork with where we have the benchmark, we have the insights, and solid numbers to target and improve on, right? And that's where this next work comes into picture. We have this assisted few shot learning, and what that means is, in a nutshell, previously we were trying to give some examples, some random examples, but giving example randomly is not the best thing you can do, right? But we don't know what the best example is, so it's kind of like a paradox. So actually, let's look formally how it was done before. We had this input image, we had this random selection of images with the correct labels. We just feed them to the prompt, and and that's where what the LM would classify. But now what we propose in this one is that instead of just feeding randomly, let's look at our input image, and see how similar that is compared to all the images that we could potentially give as input. So what's the way to find the similarities? That you encode your image, you encode your all the potential examples that you can give, and just find the distance between them, because at their embeddings are just numbers. You can just find the norm between them, and then get the top k. So those top K, those are the most, they are not guaranteed to be from the same categories. And we know that if it is from the same category, the models would be able to learn the better, but they're not guaranteed to be, but that's fine. Because as we have learned, these models are able to separate those irrelevant examples. So we're going to do our best effort just to give it the examples which look as similar, with intuition being if they're similar, they're going to be of the same category. And if there is the same category, then the LMs or the vision language models specifically, they are able to learn a lot better from those. So that's the hypothesis. And just to illustrate, what you see over here is this task, bean leaf lesion task. And if you give it traditional examples, what you see is the categories: this image, this image, this image, this image. So this is a real example that was picked from the previous work, where things were just fed in randomly, and their labels were angular leaf spot, another one, and then healthy. But we know the ground truth, and the ground truth is bean rust. So we want, and there's no bean rust here, so it's not expected to help the vision language models. The language models, we can rely on it to discard this information, but it's not going to help it. The way it's going to help it if we feed it the similar looking examples. So that's where this VIT based, and I'll explain to you what that is. Here we are feeding the similar examples. So this is the real first incident on the same data set, the examples that it picks, after we pass it through similarity check first and smartly introduce the examples into the pipeline of in context learning for the vision language models. So this is bean rust, bean rust, bean rust, and only one of them is angular leaf spot. So on paper, it's making a big difference, but do these numbers really translate at the end in performance as well into the F1 score? So that's what's represented from this. The baseline from the previous work, that's this dotted line that you see over here, on average. Of course, we are only concerned with the identification problem as of now. So only F1 score is what you will see. We have this soybean seed, soybean diseases, mango leaf disease, and then there will be weeds here, insects here. So all those data sets are coming in here. And this dotted line that you see is the baseline from the last work for GPT-4o, because that's the model that we saw was performing best compared to all the other models. And so that's what we choose. Okay, if that's what's performing, is able to learn the most and performing better, then uh, let's validate our assumptions with that. So yeah, that's the baseline. And what you see, these lines are the embeddings from the ResNet, from the visual transformer, and from the clip encoder. So these green, orange, and the blue line that you see over here, this is what it is. So as you can see across the board, let's just pick one. let's see the orange. Well, the model is able to perform a lot more, is able to get a lot more similar categories, right? Than the baseline was able to. This is the baseline, and now this is the same category examples as we saw anecdotally over here, but on average across all data set, this plot can show you that this is how much these examples are being fetched from the same category, right? And so as you can see over here, for 8 shot it's able to get about 4 examples from the same category, and that's a very good number. And you can see how this translate to the final prediction score that we get, which is that the visual transformer that's able to take the score all the way up to 80% with the maximum full throttle 8 shot examples, and it's able to perform better a from 6 tasks out of those 7 identification tasks that we discussed in the ag-eval previous work. So, so that's a clear uptick of about 12 absolute percentage points if you feed the examples that way. And this is the F1 score, which looks quite similar compared to that because there's a lot of correlation. So this is the final F1 score, and it soars in almost all of them apart from just a few exceptions. There we have other factors playing in, but in a lot of different tasks under normal circumstances, these models, which is GPT-4o here, is able to learn better if the models are comparative models were just fed random examples. So, so yeah, that was a simple illustration of how you can use the insights from those paper, and there's a lot of them there, which you saw. And the hope is that community will really build on that and use it as a base for future work. And what you see over here are the illustrations, just like this one that we saw, of how the examples were chosen in different data sets. So this was for the bean leaf lesion, and this is for the insects, for weeds, for durum wheat, and all of that. And what you see consistently throughout is that uh, if the examples are chosen smartly, then they are from the similar category, right? And then that does translate down the line to better performance. And these are all the real examples from the first inference that we do. So they are not cherry picked, but you see the trend across the board that they do perform better throughout. So so yeah, that was the work, um, and as I mentioned before, we hope that we'll continue to build further. There's a lot of work in pipeline right now. We are hoping to get it out soon, and I'll be at liberty to say more about that later. But yeah, there's a treasure trove of insights, and the new tech is very exciting. There's so much that could be built, not just in agriculture, but a lot of different things, and it pays off to understand how these things are working. And that was the goal with this work, and I really hope you enjoyed it. If there's any questions, Koshika, or anything else from me, just please feel free to speak.
Yeah, sure. So I'm back. Thank you so much for the wonderful presentation. I'm gonna actually probably kick off questions with a personal one. So you talked a little bit about in the beginning. Obviously, this has a really wide application with respect to the agricultural industry, at least in the US. So we're talking about, 5% of like the largest global GDP. So I was wondering if you could share with us maybe a more specific application that you had in mind where this research would really heavily apply. So I understand that there's a lot of important things that you can choose from, but if there's anything that you specifically were thinking about, that would be really nice to hear about.
Um, yeah, I mean, so I was just in Arizona for the conference WCB, which is where this paper was published, presented, and there I had a lot of people who came up to me um, and uh, and explained to me. how it could be used in different domains. So so one of the example that I remember vividly was that yeah, this is the different kind of automotive parts and we have different kind of damages. Can we classify based on that? So so it's like across the board. Or if you want to identify, and there's work going on at Iowa State right now on that, different kind of cancer cells, right? From just few examples, because if you want to get a surgeon or physician to be able to annotate that, well, you're gonna need some big pockets to be able to do that. But can you do that with just three examples? Well, that's what's being demonstrated right now, and I think these models they have very cross-domain applications.
Yeah, I think that's very cool to hear about. So it's yeah, so we're in kind of the agricultural space, but really the images themselves, as long as they can be kind of classified,
Yeah.
it's not too different. So in towards the end there, you kind of talked about a little bit about your further research. So I just want to maybe give a little bit more time to that and ask you about so you're kind of playing around with like certain dimensionality and data manipulation that is kind of like maybe feature engineering. So maybe I didn't understand that part too well. But yeah, so any further research that makes the images a little bit more, I guess, computer friendly, such as doing filters or anything like that, that would be nice to kind of hear about. I know we're talking about where we have some more questions actually, but yeah, no, maybe we can talk about that.
Yeah.
So the question is actually, yeah, what do you think is the next step in improving accuracy even more? So that's probably what you're working on right now.
Yeah. Yeah. So I'll give some spoilers. The next thing would be um, that instead of just looking at the images and looking at the similarity, uh, well, you need to use some external information that could drive the selection of those images, and that's very application specific. Because that's where you drill down to the agriculture and see, okay, what's the metadata about these images that I can use to be able to better classify. So yeah, that's one thing that could be done.
So yeah, in addition to the vision transformer, which is really impressive that you could get it, improve in accuracy by 80%, which is almost like unheard of. So that's really impressive stuff. So thank you so much for sharing. I think we're running just up on time. So yeah, so like I kind of plugged in the beginning. Can you talk about where you're kind of active, where if people want to connect with you if they have some similar research, whether LinkedIn or whatever platform you prefer. You could give like a summary of where you can be found essentially outside of your research that's published in like NeurIPS and some other places, WACB, I think. So please do look at our guests, our Bob's research there. Yes, there's anything you want to plug really quick, please do.
Yeah, I mean, I'm very open to hearing any thoughts. So if you want to reach out to me, it's arbab, ARBAB at iastate.edu. So yeah, just reach out to me. Give me an email. I'll be very happy to hear, discuss any ideas uh, or thoughts or brainstorming. Um, but yeah, or I'm also on LinkedIn. If you want to reach out to me there, just connect with me there too, and just have a look at those papers. I think they are very good paper. A lot of work went into that, not just from me, but a lot of different people. As I've mentioned before, Dr. Samik Sarkar, Professor Bhaskar Ganapati Subramaniu, Adarsh Krishnamurthy, Dr. Chinmay Hedge, and a lot of different people actually, Dr. Arti Singh. So it has been a very collaborative work, and I really hope that people see the agriculture as being the use case. Few motivating uh, examples coming out, which are really fruitful and could really be deployed at the end, not just fancy numbers. And that's why we are working currently. It's an app called Pest ID. We're trying to integrate everything, right? We're trying to eliminate this problem that ChatGPT has. If you give it a pest, it might just call it a butterfly. So you want to ground that. And the first step is to be able to build those modules that you can feed into your tools, into your models as tools. So kind of like distributed agents. But these are all the building blocks. We are working on that. And yeah, just if you have any things for me to look at, and I'm sure you do, just shoot me an email. It's arbab@istate.edu, and I'll be very happy to connect. And very grateful to Koshika and Garsky, you as well, for coordinating. A lot of work went into that. Thank you very much.
Thank you, thank you. Oh, thank you for the bonus content at the end. So we'll be on the lookout for any development on that end as well. So thank you. I think with that we're gonna close it out for today. So thank you so much again, Arbab. Really nice presentation, really nice work. And we hope to keep in touch with you. As well as keep get in contact with you as well. For those who wanna probably have a word with you and talk more about the research. So thank you so much, and I guess we'll see everybody next time.
Thank you. Bye bye.
Bye, guys.
Bye bye.